my pleasure to introduce today's speaker, Professor Rebekah Sweat from Florida A&M University, Florida State University, joint institution. Rebekah graduated from exactly the same institution in 2015, after which she worked for Scalable for 3 years. And then she turned back as an assistant professor. So in addition to Florida State University and the FAMU, she's also a member of the High Performance Material Institute located in the same campus. And I suspect that most of the work that she's going to show today is done in the institute there. Rebekah specializes in computational modeling, mechanical analysis, scalable manufacturing, fracture mechanics, with emphasis on advancing hydrocarbon composites. And the subject of today's talk would be on boron nitride nanotube materials. Thank you very much.
Awesome. Thank you. Thank you, Tryon. And thank you everyone for having me as your seminar speaker. I'm looking forward to some interesting discussions. So we have some similar research areas as some of your professors here. So looking forward to developing this relationship closer. So he gave a thank you for this excellent introduction. So like you said, I'm from the FAMU-FSU College of Engineering. It's a joint college between Florida State and Florida A&M University. So I have students from both universities that we all work together. So I'm assistant professor. I've been there for about 4 years. So these are some of my students. I put them on here just because they did most of the work, right? So yeah, as graduate students yourself, right? You want to show that this is my research team. I have a picture of all of us at the end. So these are some of my group that's contributed to this work, mostly in boron nitride nanotubes. I'll show you more about that in this talk. So the overview me. So the first couple slides are just overview of a few topic areas that I've worked on previously, and then I'll go into more in depth some of the work that we've been doing with hybrid nanocomposites. So here's some collaborative work we've published with Sandia National Labs. This gives a kind of insight into the combined modeling and experimental approach. So we put in hexagonal boron nitrides particles and silica phenolic composites to look at the thermomechanical performance. So we did some under flexural testing. We made some digital models of the flexural testing and did a triple scale model where we have, this is the global scale 3-point bend, the middle scale woven carbon fiber phenolic, and then inside this scale is the hexagonal boron nitride particle. So in every model, you've probably taken some finite element classes. So each of these has a number of finite elements that each one of these are embedded directly into this this is the global model and these two local models. And each element of the matrix has a direct local scale embedded inside of it. So this is what you call like a true multi-scale model. So not doing like homogenization over the entire structure, but true multi-scale. So we can actually dig out what the real stress levels are at the individual points. So here's, and then we can also match up and see how close we are with the virtual stress strain curve and our experimental fracture patterns and things like that. So this is that's one example of some of the work that my group has done. Here's some of my group in the lab. So this is clearly taken a couple years ago. So had to face masks. So this project I won't focus on right now because that's one of the ones I'm going into in more in depth. But we did some SLA 3D printing of some nanocomposites with boron nitride nanotubes inside of the ceramics. So SLA 3D printing with ceramics is pretty tricky. So we developed some of our own inks. And that's one of the areas of future direction is developing more high temperature ceramic inks in-house. So that's one of the projects I'm gonna be going over more in depth. Some of the other work that I've done, so some of you guys can probably appreciate this one. I have no background in perovskite solar cells. That being said, when we are all sent home via COVID, everyone wanted to do modeling. So we figured out a way to develop some representation and model of a perovskite solar cell, based on the different perovskite crystals, the grain boundaries, and then the different structures underneath it. So a perovskite solar cell is nothing but a composite, but just made of different electronic materials. So we also did some in situ microscopy. So we have an in situ mechanical test frame that you can put inside of a scanning electron microscope, so SEM. You can do SEM at the same time as you do bending. And so we were able to, these are 3D models on the bending and cracking patterns based on the different crystal arrangements. And then they showed pretty good alignment with the last two are SEMs of the exact same structure. So the whole point of this is to develop flexible solar cells. So yes,
Is that hybrid or oxide? The
is
perovskite is a hybrid or is the
it's a
oxide?
hybrid.
Hybrid.
Yeah.
Okay, so
Mhm. So these are some that we make in-house. I don't make them, but in Florida, it's hard to make really good solar cells because of the humidity. But but they can do some good ones under a glove box. So it's some spin coating. So we also have, my group has a Siemens partner grants that we work with Sim Center 3D. That's one of the finite element packages that we use to make some of these 3D models. And they have a pretty good multi-scale module and also some cracking algorithms that we've embedded some of our own cracking methodologies inside of. So here's a previous paper on that was using the X-ray inputs from a carbon fiber to look at the crystal size, despacing and rotation, to input those into a global single carbon fiber. So this is a single carbon fiber that I did compression and tension on, and this was in order to use modeling to look at things that we can't do very easily experimentally. So that's one of the benefits of modeling is trying to do things that is very difficult. So it's near impossible to create perfect pillars of carbon fiber that's 5 microns in diameter, and create perfect pillars and have perfect compression and tension without having any kind of mismatch in your test setup. But you can do that pretty easily in simulation. I can draw a cylinder, I can pull on it, I can push on it very easily. So this was studying the different process parameters like crystal spacing and crystal size and their impact on total carbon fiber performance. And that's in relation to, I did this work partially with my previous company, worked at Solvay, a manufacturer of carbon fibers. So we did some of the work with precursors and tuning the different alignment processes and crystallization temperatures to make make these sizes. But one of the questions while I was working there is which of these parameters actually impacts the modulus and strength the most, and tension and compression. So this helped answer some of these questions. And now I'll get into, I guess, the more of the meat of a few projects, but I just wanted to show you kind of some of the breadth that we do over HPMI and FAMU-FSU engineering. And now I'll get into, these are projects that we've done in the past, it's a year and a half. So very exciting recent work. And so they're in relation to boron nitride nanotubes. So you may have heard of carbon nanotubes. Carbon nanotubes are something that's been studied over the years very well. So boron nitride nanotubes have the same physical look. So this is the SEM we took back in 2022. BNT, it looks exactly the same as CNT. You couldn't tell the difference unless you knew what was in it. So the same kind of like wavy and tangled structure. You know, these are definitely going to be bundled tubes. And the major difference is that BNTs and CNTs, they're both thermally conductive. BNTs are electrical insulators and CNTs are electrical conductors. So it kind of flips that property. And the BNTs also have higher oxidation resistance. So at those high temperatures. So some of the work that I'm going to be showing today is trying to take some of these beneficial properties that we know that they have and use them in a composite structure and analyze how they perform in these extreme environments. So these is kind of some comparison between BNTs and CNTs. There's less is known about BNTs and CNTs. They weren't mass produced until much later than CNTs. So based on some of those attractive properties, we want to see where best we can fit with these attractive properties. So high temperature space instruments, electronics, drug delivery are some of the applications where they could be attractive. So they're thermoconductive, electrically insulating, like I mentioned, but they're also radiation resistant. So especially for space applications, they're a really good candidate for protecting devices. And the high oxidation resistant could be something like rocket nozzles, nuclear protection suits, hypersonic travel, a lot of different areas. I'm not anywhere in the area, anywhere near drug delivery, but it's also been hypothesized to use them as drug delivery agents to put the drugs inside of the hollow tubes and then open the tubes. So the body is, so BNTs have a very low cytotoxicity level, so you can more easily put them inside the body without adverse effects. So here's that's some ability. So where did we start? So this is a couple years ago. So the BNTs obviously demonstrate some potential with ceramic matrix composites because of the high temperature resistance, but we were trying to put them into ceramic matrix, but in the ceramic matrix, you need to know what temperatures to center at. So when you are putting in your centering parameters, the question that I posed to my students, so it's wonderful, there's a lot of students in the room, I said, so go find the literature that tells me how high they can go. So my student came back to me and said, I can't find it. And I said, well, you're not looking hard enough. Look some more. He said, no, it doesn't exist. We know where they degrade in oxygen-rich environments, but we don't know how they degrade in inert environments, which is how CMCs are manufactured, and also in inert environments like deep space. So it didn't exist. So I said, well, we need it for we need it for manufacturing. So go figure it out. So go do it in the lab. So a student, Mehul Tonk, last year, he did the decomposition of BNTs and found that they're pretty stable up to about 1800 degrees C in inert environments, briefly stable to about 2200 degrees C, and observed a stable tubular structure via transmission electron microscopy, or TEM, after exposure to 2200 degrees C heat testing in a real manufacturing graphite furnace. So not just in a TGA or something like that. So and so upon very thorough, this is published work if you're interested, upon very thorough investigation, the decomposition was with unzipped walls, damaged walls that initiated at defect sites, initially at the high temperatures, and would unzip a wall. So these BNTs are anywhere between 2 to 10 walls. So even though you have retained tubular structure, some of this amorphous material you can see at the surface could be unzipped walls that have happened on the surface. So we've demonstrated why why they're a good candidate for some of these properties. So the first project I'm going to be showing is printed ceramics with BNTs. So we are choosing these because of their potential toughening mechanism. So toughening, they're very small nanoscaled reinforcements. So when a crack is formed, they have potential to be able to halt this kind of crack. This is traditional toughening mechanism, and you can see that through this SEM. So this is some of our equipment. This is high temperature CMC manufacturing and sintering ovens. Printed ceramics were done through in-house SLA printers. So the process for making these nanocomposites, so printed ceramics are nothing necessarily new. So printed ceramics actually are in the textiles industry for like jewelry. So there's a lot of printed SLA, non-engineering ceramics that you can get off the shelf. But our challenge is to incorporate these nanofillers into the inks, so you have a nanocomposite rather than just the ceramic. We want to have those, nanoscale toughening and the nanoscale thermal spreaders as well. So this will help with high temperature applications. So we put it in DMF, magnetic stir, bath sonication to break up the BNT clusters to be able to get a really good dispersion. Put in the silica filled ceramic resin. This work was done with silica, fused silica as the ceramic. This is not a super high performance, I would say it's a middle performance ceramic. Based on these results, we actually, as of last week, have some promising results with silicon carbide. So silicon carbide as the ceramic, swapping out the silica. So this was just something to prove feasibility. So, and then did the SLA 3D printing. You can see the SLA 3D printing here, the complex geometries with very high resolution, polymer burnout at 750C, and ceramic fusing in nitrogen at 1275. And then we did some flexural testing, DMA, LFA, which is thermal testing, and SEM. So, and through the previous study, this all builds on itself. So through the previous thermal decomposition study, we know that our BNTs are safe at these temperatures. So we don't expect any degradation to happen during the processing. So we want to understand the fundamentals of the 3D printing. And so when you do 3D printing, you can do them in different ways. So we studied the 3 different ways of additive manufacturing in type A, type B, and type C. So growth along length, width, and thickness. And then we studied them in a 3-point bend flexural testing with those support beams, as you can see here. So here's our porosity. You can see that it clearly has some porosity from single shot burnout. Traditional ceramics are done through more reinfiltrations and additional sintering cycles. So that can be done. So overall, the mechanical testing showed that the toughness increased about 18% with only 0.1% weight filler. This is not terribly surprising because we know that we have these very long high aspect ratio fillers, and we saw that toughening mechanism between that bridging, which we'll see we'll see as we further do this investigation. So you can see A, B, and C. These are the different types of printing. So clearly types B and C, based on beam theory, we've done it all in class, can have the most promise as far as modulus and strength. Because type A, you're pretty much looking at like the 90-degree testing. So overall, pretty promising 18% toughness increase with very few, with only a very small amount of filler. So you can see these are the 0.1% weight BNT. So clearly with a one-shot burnout ceramic, you're going to have porosity. So you can see even with these porous structures, you have BNT bridging across the pores, which is which is why we have those increases in properties. All right, so thermal diffusivity, we studied them at laser flash analysis. So thermal diffusivity, this is I think one of the most exciting enhancements. So we have a significant enhancement of 62% higher thermal diffusivity. So with only, again, 0.1% weight BNT, which has great promise with more high temperature ceramics like silicon carbide, silicon nitride. So you can see that increase is likely due to the manufacturing parameters of paying close attention to the good dispersion. So we know that when we're looking at a BNT, we have low thermal resistance across these planes, which is in the direction of the tube, and high thermal resistance across the different walls of the tubes. So when you have a good dispersion, this will spread the heat more evenly and allow us to capture the properties of the thermal conductivity. All right, so this kind of leads back to the initial modeling part. So when we're modeling CNTs or VNTs, you can see that they're not just like straight sticks. So we can't model them as sticks. We can't model them as particles. So we need to model them as they truly are, which is like a wavy and tangled structure. So this is continuum mechanics. So we're using this is an algorithm that some of my students came up with, and they coded this in Python and put it into SimCenter 3D for automatic generation of wavy microstructures using different parameters like regions, waviness control, and the closeness of a tube to the other tubes, and it will automatically generate video. And it'll automatically generate based on the diameter length, waviness control parameters. It will automatically generate your representative volume element or your RVD that you can input into these multi-scale structures, which is exciting. You can have a very complex structure with some randomness, which you would see in real life. Okay, so here's the more recent. Here's the more recent work. I've got 25 minutes left. So the extreme performance of hybrid nanocomposites. So all of this is in the area of boron nitride nanotubes, the BNNTs, but we look at them in printed additive manufacturing settings with ceramics. Now we're going to look at them hybridized with polymer composites, polymer fiber reinforced composites. So we have taken these BNNT puffballs. This project used unpurified puffballs. That's why they look brownish in color. So highly purified BNTs are kind of a white translucent color. So they have some interesting optical properties that I've been discussing with some of your professors. And we take these puffballs from BNT materials, we solidicate and break them up into a well-dispersed solution. We use vacuum-assisted filtration, and we create what's called bucky paper, or like a veil of like a BNT veil. And then we can use it in standard autoclave curing cycle, standard composite processing from there. So it's handleable. It's like a regular sheet that you can easily handle. So, and then we process these with other standard composites. So we have carbon fibers. We know the properties. We have BNTs, which we've just gone out over, has some good attractive properties we're trying to employ. And the matrix was 977-3 toughened epoxy. So toughened epoxy means you have a thermoset, and you also have thermoplastic mixed inside there too as well for additional toughness. So the exciting part about this, we received this 977-3 from Solvay, my former employer. So I know from working in the industry that the customers really like the toughened properties of the 977-3. This is one of the more popular resins that commercial aerospace. But the challenge is this is not an extremely high temperature system. So the challenge here was, how do we take a traditional composite system and use it in extreme settings and figure out a way to protect these nice properties of a matrix that we like, but in extreme settings. So in this study, we did meet, so this carbon fiber 977-3 prepregs, has a 8 stacking sequence. In one of them, we put 1 layer BNT sheet, and then the next one we put 2 layer BNT sheet at the surface. You can kind of see where we're going with this. We did some flexural testing of these composites. So you can see that the addition of the BNT layers inside. I didn't put those on there. We also did interlayer ones. BNTs on the interply reduced standard deviation of the bending modulus and strength by around 84%, but didn't really change the properties. That's not necessarily a bad thing, because we don't have increased modulus or strength, but we don't have drop either. But we have a significantly reduced standard deviation. That was going to be there. Sorry about that. Going forward. So now we take those surface layer. So the surface layers, we're trying to protect the structural composite behind it, right? So how do we test that? We put in, this is a torch test. So we we have our sample here that's clamped in these steel molds. We have 2 thermocouples connected to the logger, attached to the back of the sample, and then a 1-inch torch outlet in front of the sample surface, and then we turn on the torch and torch our samples. You can see here's the front side temperature. We're clearly burning the surface. This frame was made to control where the damage was made. So you can see that we have some smoking on the back side. We have flames on the front side, and then, so if you guys were asleep at this point, here's some fire. And then we did some characterization and studied the temperature and weight loss before of this test during and after, and then looked at it under SCM to see what kind of things we got from there. So very exciting results. So these are temperature plots based on time. So we had 105 second exposure under flames. So this is the temperature plots. We have time. We have the meat is in blue, 1 layer is in red, 2 layers in purple. So the benefit, the promising kind of thing we're looking for is we want that backside temperature to be as low as possible. So we don't want the temperature to have gotten to the backside. So because the backside is where we have our structural materials, we don't want to burn that. Imagine you're in a space vehicle and you're on the back of that. You don't want it to be over a certain level. So the exciting part is the 2-layer had almost 40% reduction in backside temperature with only 2 layers of addition. So a very small amount of added material can really result in a pretty large backside temperature reduction. So you can see this neat 1 layer, 2 layer. Here's some, I guess maybe surprising results. We showed that this is the weight loss percentage. So we also assume there may be some added benefit of having less weight loss or less bulk that's lost from this ablative testing. And so the neat lost 14.1%. 1 layer had a significantly less weight loss, but the 2-layer had about the same. So upon optical microscopy, we denoted that that the 2-layer had some dry surface layers that then peeled off, which contributed to this additional weight. We're planning on setting that further by increasing the matrix content in the surface to better adhere the surface to the structure. So the results post flame test surface morphology. So we can see showing depth, so multiple layers, even inside these one layer BNNTs, you actually really have multiple layers inside of them. So you can see multiple layers are exposed. So you do have charring up at the surface, and you have so we have like a scaly platelet on the top surface. What we're going to do more investigation as to what that is in the future slides. And then we have some charred epoxy. So with an asterisk to say this is likely thermoplastic. So epoxy and thermoplastic together, the epoxy likely would char off, but the thermoplastic would create this kind of veil. So this is likely the thermoplastic in the toughened epoxy that we have. So we have that charred epoxy that are really thermoplastic, and then we have charred rods of potentially PNNT thermoplastic. These are too large to be individual BNNTs. So something else is happening here. And this is also the subject of our future work. So the exciting part is here's some more SEM. So we have these kind of crystalline structures that formed from potentially the BNNTs. There's nothing else there, so they had to have formed from the BNNTs. But they're very odd looking structures. I actually got a call from my students at the SEM saying, I have no idea what we just found. We have no idea what we're looking at. And so we have some really unique kind of crystalline structure, but underneath this melted thermoplastic layer, you can still see intact BNNTs. So at least from that 105 second exposure, we don't have full loss of that protective layer, which is potentially a good thing if you're doing some like reentry into atmosphere kind of studies. And further studies of this flaky layer platelets, they're really very large, like full flaky layers. And if you've ever seen SEM of rose gypsum, it looks kind of like that. But that's clearly not what that is. So we have a layered structure with these distinct morphologies, large stack platelets, rod structures, intact BNNTs with smaller HBN platelets. So the next question is, what are they made of? So we did some EDS to find out what the chemical composition was, and saw that there's your charred platelets and here's your rods, carbon / boron, because carbon and boron can be sometimes difficult to distinguish with EDS. So that's carbon / boron, oxygen and nitrogen. So the platelets clearly have a very high oxygen content, but they still have nitrogen, which means we still have the existence of BN, which means that this is likely protective B2O3. So we can make some of those conclusions from EDS, and then the rods are primarily carbon or boron. They don't have high oxygen or nitrogen content, so right now we're a little unclear. So potentially just amorphous boron. So and then further, we want to find out more what those crystals are. So FTIR has revealed that they have characteristic boric acid bonds, and then the XRD shows the crystalline H3BO3, which forms from that B2O3. So we've kind of discovered kind of what these crystalline surface structures are creating from FTIR and XRD. So exciting that we have a potential not only manufacturing method, but potential material that can protect from these harsh environments or these extreme environments and still maintain their structural stability. So the conclusions from this part, and then I will go into the last and final sub project here. So the 2-layer B&T have maximum backside backside temperature reduction of about 40%. And a 14% weight loss due to flame exposure. And we can see what types of boric acid resultant crystals that we have found at the surface. This could be something that we're doing some future studies as to how these are formed, and also the potential for like a structural char, which would be really exciting. Like I said, the last and final sub project here is related to some this is kind of our motivation, is our deep space exploration requires these better materials. Reentry vehicles experience these conditions. So we just showed temperature. So they're experiencing high temperature, but what else are they experiencing? Other things like radiation, but they're also experiencing high pressures. So that propane experiment was done under no pressure environment. So the combination, so you learn from thermodynamics, the combination of pressure and temperature is extremely damaging. So we need to look at the aerodynamic loadings and the high heat fluxes. So we did pretty much the exact same processing parameters, but this time we're using a phenolic resin rather than a toughened epoxy. So we're using the Durite SE1008 phenolic resin. Otherwise, we are using a woven 97 and B&T sheets prepared the exact same way in-house. These are the manufacturing parameters. We also have surface layer B&T and interlayer B&T, which you saw as well. So you have the ones on the interfly and surface layer, and then you have neat ones without any B&T. So how can we simulate these reentry conditions on the ground? So we want to do them in arc jet or plasma wind tunnels. So we are lucky enough to have some friends next door to us. So we have the FSU FCAP, Florida Center for Advanced Air Propulsion, about 30 feet away from my lab. So it's clear where we're going next. So we're looking at these reentry conditions. This specific is a hot jet, combustion driven supersonic wind tunnel. There's an ethylene based burner. Up to Mach 2.5, outlet gas velocity at 1700 degrees F. So we're going at 1700 degrees F at Mach 2.5, and here's our core little sample. The jet exhaust. So this setup has previously not been used for materials characterization. So the FCAP facility typically does work in flow and CFD and acoustics, those kind of analyses, not typically for materials. So this is a good opportunity to develop some devices to also go inside of these hot jet facilities. So these hot jet conditions, like we just mentioned, we have 1700 degrees F, about 2 atmospheres, and this one we only have 10 seconds of exposure. So we did these characterization methods. Here's some more pictures of the hot jet facility. Here, the jet outlet, we have an IR camera monitoring the surface temperature. We have a thermocouple on the backside of our sample, pinned on the backside. We can track that. We also have a sample holder that once the jet is at velocity and temperature, the sample holder inserts our sample into the flow for 10 seconds and then drops it. So that way we don't have any residual effects before or after. Here's our poor little sample getting hot. Make sure this was muted. This was very loud. And then drops away. So the thermocouples measure the backside temperature, optical cameras and video recorders, and the IR camera measuring that front side temperature. So here's the video from it is going, probably from the video from the IR front side camera. So you can see we could actually track the exact temperature of the front. So here's a summary of measured front side temperatures. We have the neat, we have the inner layer, we have the surface. So 1 second, 5 seconds, 9 seconds. You can see this is the surface layer being achieved, this interlayer. This is the ones without being achieved at all. You can see that there's some increase in heat signature on the surface of the surface layer being a T. We don't at this point know if that's a good thing or a bad thing yet. It could be that it's isolated there and not transferred to the back. At this point, we don't know. So we again have the measured backside temperatures between the neat, the inner layer, and the surface layer. Very different from our last finding. So this is heat and pressure, not quite as hot as the propane, but under pressure. So the pressures can cause some kind of wacky things to happen. So zoomed in, we can see that the inner layer actually shows the highest temperature and the neat shows the lowest temperature. Not exactly what we want, but it's interesting nonetheless to further study. So it basically shows it doesn't negatively affect it, but it doesn't really help anything. So in this case, it doesn't really help anything when we have the high pressures added to the heats. So we have, and this could be due to the high thermal conductivity of BNTs. So potentially. So but what we have found is that they do mitigate ablative weight loss in the pressure. So they don't reduce the temperature, but in this pressure environment, they do mitigate the weight loss by at least 1% lower than the neat. So whether that's good enough, unclear, but the interesting part as well is the surface layer hybrid morphology. So the surface layer of these composites show a really unique morphology. So if you think back at what we looked at with the crystal structures of the propane torch testing, we saw these really big crystals. We still see some of them in this case a little bit, but we have this is a different matrix. It's a phenolic matrix that's known very well to char. So it's actually used as a precursor to carbon-carbon composites quite a lot. The phenolic is the 977-3 toughened epoxy is not ever. So this extensive char layer isn't necessarily a bad thing. It looks much more structural than the last char. It looks like much more of a structural char, but you do have nice bridging between these char layers. So kind of holding them in place. So that's not to say that we're without these wonderful little crystals. So these little crystals have followed us. But if you can actually see in the char layer, you have this micro crack in the char layer. You can see bridged being achieved across the entire thing. So really nice toughening mechanism, potentially even after these extreme environment events, that is potentially further toughening them. The same kind of crystals that we know, that now we know well, are species of B203. All right, so we have this is before we did the other studies that further narrowed down what they were. But these various forms we have in this case, we have much larger diameter crystals than happened in the previous, but less stacking. So less stacking, but larger ones. That's still a little unclear of how they form. I've actually been discussing with some potential collaborators here to study how that happens, how that forms. So this is future work to be done for sure, but very interesting product forms that go from a wavy integral nanotube structure to a crystalline a crystalline oxide, so. Here's more EDS that does correspond to the same as the previous analysis to B2O3 and boric acid. So these forms are likely the same kind of crystalline forms. All right, so I think I'm about hit my time. In summary from the work, we've done a lot of work with BNTs, not only with their potential for additive manufacturing and advanced manufacturing techniques, but also looked at how we can put them into structural layers of composites to not only mitigate temperature, weight loss, radiation shielding, and is potential as well, and seeing how we can use product forms. So this is a manufacturing advantage, is to have product forms that you can readily add as a surface layer to existing structures, and help us reach further deep space travel, hypersonic travel, reentry performance. So definitely want to thank my team. Here's the folks that did most of the work. So there's some of the team, this was taken in the summer, and not pictured is Aspen Reyes, who did most of the hot jet work, and Kalia Gant, who did most of the propane torch test work. And Aspen is funded by San Diego National Labs. Kalia is funded by Merck. And Aspen also got the Amelia Earhart Fellowship this past year. And so we have lots of friends. We can only do this together as a large group with various backgrounds in chemistry, mechanical, and modeling. So I want to thank everyone for inviting me here, and I'll happy to answer any questions.
Thank you. Thank you very much. So are there any questions? Yeah, go ahead.
In terms of the thermoset with BNNTs, have you done thermogravimetric analysis by any chance to observe the decomposition weight loss under a controlled environment?
Yes, we have done. That was actually to determine what the weight percentage of the BNTs that we had. The decomposition was, I think, around 350 degrees C. So, but under a more controlled but extended periods. So that PGA would take it up to about 1,000 degrees C, and we held it until we had that decomposition. But yeah, it does decompose it under lower settings when you put the entire sample in there in a small amount. Does that answer your question?
Yeah, and then a follow-up question on that is, do the decomposition products directly result in the nucleation of the crystalline oxide structures that were observed from TGA? Do you see any hexagonal structures?
We did not observe them. So that's something that is very interesting. I don't know if we didn't catch them, or if that's just something that's formed by those very intense heat signatures on the surface that from the heat flux. That's definitely something that's interesting. The heat flux may have a role there in the formation of this crystal. That's a great question. Thank you.
Yeah, thanks, Rebekah. That was really great. When you're constructing the representative volume elements of BNNTs, I just wasn't too familiar with how that's done. Could you give more details? Do you control like the BNNT diameter distribution as well as the curvature in them? And how do you know that you're recovering then bulk properties for that RVE?
Let's start with this first.
Mechanics question.
What?
It's a mechanics question.
Oh, yeah.
I don't know when mechanics.
I think he's right. Yeah, so you have prescribed diameters, lengths, waviness controls. So you can put in whatever periodic conditions you want as far as diameter, waviness, sphere, upper, lower, re-entanglement. So you have basically full control.
Okay,
Does that answer that part of the question?
part of it, but then how do you know that this will truly be representative in terms of the properties?
That's a great question. So this is just, so we can do them two ways. And that's where there's a little bit of ambiguity between the mesoscale modeling that Tryon does. And this is obviously solid mechanics. So we have to follow solid mechanics rules. These were constructed as solids. We know that they're not solids. So you have some uncertainty there. But typically what we would do is find out whatever volume fraction we have here, match them to whatever mixture that we have, and then use those properties.
Okay.
Is that?
Yep.
Yeah, kind of answer. Yeah, so there isn't some uncertainty. We can also form these as hollow structures. But we do not have the same kind of like atomistic control that a molecular dynamics or a mesoscale would have. They're going to just have as best as we can represent them. So would be like what 1 terapascal modulus in one direction. That whatever Poisson's ratio, I think 0.2. And so it would be limited by the inputs of continuum mechanics, which can be helpful in some cases, but is a limitation. So I wouldn't want to study anything like intertube dynamics on this, but like deformation, fracture, slippage between interfaces, that's also something. So just figuring out what you can study based and what you can't. But like I said, we can do these hollow structures or solid structures. With walls, with hollow structures, you're going to have a lot more elements, so you're gonna be limited as to how big the model you can make it if you're assuming that they're kind of those thin wall shells. But this is probably as close to the smallest scale that I'd be comfortable at, just because you are losing some of those like atomistic potentials. That's a good question.
Yeah.
I have a couple of very simple question. In your hot jet test, right? When the 1700 Fahrenheit hot jet is coming, I was expecting to see some sort of a shear effect, right? I did not see any jet coming, and why is that? Is it because of the anechoic chamber was kind of higher?
Two things. Anechoic chamber was doing its job, and two, it had already reached equilibrium. So it takes a couple minutes to reach equilibrium, and that's when we started our video. So once it did do that, right, when you turn it on, but once it reaches that equilibrium state, it looks fairly boring.
I see.
And then we enter we put our sample up into that.
Okay, but you do see when the transient happen, right?
Yeah.
Okay. And then there's another, like a very, how hard it is to, manufacture this boron nitride, this nanotubes in a very complex shape.
Pretty complex shape.
So like, in terms of like complex, like, part that you want to manufacture for hypersonic vehicles, how hard it is to use this and manufacture that complex part?
It's as difficult as like a traditional veil would be. So it's a thin, it's about 100, so we can control the thickness as well. The easiest one to do is about 100 microns. So it's a fairly thin, flexible veil. But at that point, it doesn't have any matrix in it. So you can add whatever matrix you want after that case. So it's a flexible veil that you can do what you want with. So you can put it as like a surface coating and then put some kind of adhesive to bond them together. Yeah, it's a good question though, because the handleability, I think in the future I'll probably put a video, like it's just like it's like a fabric. like a thin fabric. Yeah, so you can mold it around fairly easily, like a veil. Yeah, which is exciting, I think. Because coming from industry as well, industry, anytime you mention some like nano fillers, sometimes they kind of like cringe. Because they don't want to work on incorporating them inside of their polymers. Because ordering, put them inside the polymers is really tough. But using them as a freestanding layer and applying matrix is something that they're very familiar with doing. So that does kind of break that barrier of entry to potentially being more manufacturable. It's a good one.
So I have a question about specifically about the 3D printed materials that you then burn the polymer out and sinter it together. You're depositing this like wavy structure in the 3D printing. Is there like lasting effects of the different layers that are deposited in there, or how does that?
With
affect
of the
overall?
wavy nanotube, of the wavy structure in 3D print.
So is there like anisotropic like regions within the end product that you print?
That's
Layers that it might delaminate along?
layers that it could delaminate with this level, with this very low level of additive, we did not see that. You would probably see that with higher levels of additive. You also need, so this is not extrusion 3D printing, so you wouldn't expect any like orientation. You would just expect to hold whatever suspension orientation you have, and then you're just freezing it in place. But as we increase the content, it will affect the shrinkage. So when you have polymer, and so basically what this is, when you 3D print like that, it's a ink that has a UV curable polymer with some kind of particles, like in this case ceramics, that you burn out the UV curable polymers and you're left with whatever particles you had it suspended in there. So that itself has its own shrinkage profile. And when you add in another filler to stabilize it, you will change that shrinkage profile in the different directions potentially as well. So at 0.1%, we didn't see any effect. Higher than that, definitely going to see something as far, but potentially a lower shrinkage. Yeah. Thanks.
So I was wondering if you would replicate these experiments with carbon nanotubes. Okay, so, and of course with carbon nanotubes, you have a larger variety of material. Do you think would be worse than like in terms of, for example, ablation protection, or like is it better to work with BNNTs or it's the same?
With the additive manufacturing or the other one?
Yeah,
With
yeah.
both?
Like if you, I guess with any.
Okay, so the difference, so these experiments, the ablation, the flame test ones.
Yeah.
Already have been performed with CNTs.
Yeah,
They get, I would say, similar performance as this, but the intrinsic properties of CNTs have lower oxidation resistance. So ideally, they would perform worse. So they get, as far as the pressurized ones, they're about the same, but CNTs don't see this 40% reduction in backside temperature, which is likely due to their less oxidation.
so it's more, it's less reduction.
Yeah.
Okay.
There is. Okay, so in air, you have 400 degrees C temperature. This is a little higher than that sometimes, up to 800, but this is over 900 degrees C in air. So that's potentially a better opportunity for additive manufacturing. CNTs typically have a higher aspect ratio. That might be beneficial.
Yeah.
There's different properties, and depending on what kind of final property you want. So if you want those additional E2O3 crystals to act as a structural char or something like that, The CNTs would decompose into amorphous carbon. So it just depends on the structure that you.
But I guess those are not playing a role, or are they playing a role in convection? This crystals that are.
The crystals, also will protect as well.
So it's,
Yeah, as long as as long as it retains some of these crystalline and the B2O3 should be a thermal protection also. It's the question of can you keep them intact? So they don't fall off. As long as we keep them intact, they may retain that thermal barrier. But carbon has a difficulty carbon does not form crystals like this. So carbon would not have that protective layer, but you would have amorphous carbon. So for carbon, that might be fine.
yeah, my state.
Yeah.
Yeah,
Yes, regarding the hot jet test,
Mhm.
do they measure or is there a method to measure heat flux that they have?
Not that I know of. That's a question we've gotten to.
Yes, because when you want to be representative of re-entry conditions, where you have an extremely high heat flux.
Yes, I don't think we have a way to measure heat flux.
They
But-
usually use calorimeters.
Yeah, yes, I asked when we did them and they didn't at the time.
And this is just a hot air, or which gas is that?
Ethylene,
It's all ethylene.
Yeah.
And in the torch case, it was propane.
yes,
Thanks.
yes. Yes, as ethylene burner and propane.
So these are combustion product, right?
Mhm.
Of propane and ethylene.
Which is interesting, right? Because during the entry, you have combustion, but you also have gas.
I think that's a perfect setup for a potential collaboration, isn't it? You also have plasma. Yeah, so we haven't studied that at all, so that would be very interesting. And to study the formation of these crystals with their plasmas as well.
all right, so thank you, Rebecca, again.
Thank you, everyone.
The whole thing.